Hello, students. So this is the supplementary lecture that I was talking about. So I'll talk about uh, some important results in countability. So before I get started, after talking to many of you in during the last discussion class, I realized let me try to define the cardinality of set in or at least try to throw some light on it on the definition. So there are two kinds of cardinalities. So a set, um, so there are two kinds of sets really. In the first kind, you can count the elements of set, and in the second kind, you cannot count. So the sets in which you can count the elements, they are called countable. So and sets where you cannot count the elements are called uncountable. Now, what is the meaning of counting? So suppose I ask you to count your fingers on, say, one of the hands. So definitely you count like first you say you count you so I mean whenever you count your fingers, you level the fingers one by one, right? So first finger you take it out, and then it becomes the first finger. The second finger that comes out of your fist is going to be the second finger, and the third, and so on. So automatically, without even knowing it, you're leveling the fingers f1, f2, f3, f4, f5, right? That means basically you are finding a bijection between the set 1, 2, 3, 4, 5 and your 5 fingers. So counting basically means finding a bijection from the set of this uh, from some subset of the set of natural numbers to your the set where you are trying to count. So generalizing this idea, so this is how a finite as a counting in a finite set will happen, right? So x is finite if I can find so this a n I'm calling the set of all the first n natural numbers. So if x is finite, so I'll call x a finite set if if it has some finite number of elements, and suppose I'm counting the elements in x. So once again, I have to call something the first element, and then call another element the second element, and so on. That means basically counting in x is equivalent to finding a bijection from x to a for some. So and this particular n is going to be the cardinality of this set x. Now, what happens if x is not finite? If it becomes infinite. So we can still have this notion of counting, because we're just going to generalize whatever we have got, this map, this bijection that we have got from x to n. Instead of this, we'll just instead have a bijection from n to x, and then I'll count in x via because of this bijection. So for example, how do you count in n? The set of natural numbers. You count 1, 2, 3, 4, etc. So I'm going to, using this bijection, I'm going to, or I'm going to, I'm going to start counting elements using this bijection in x. So 1, 2, 1, 2, 3, 4, etc. So I'll start counting in x as a1, a2, a3, etc. Because of this bijection. Okay. So 1 not equal to 2, then a1 is not equal to a2. So I know that. So if things are distinct here, so this counting in n, so counting two distinct elements in n lets me count two distinct elements in x as well. And because since this map is bijective, every element in x is also accounted for. So this counting makes sense. Okay, so counting in n and counting in x makes sense because of this bijection. So that's why we say that x has as many elements as that of the set of the natural numbers, provided we have this bijection. If some set is uncountable, then there is no way of counting, right? So we found, so yeah, so on a case by case basis, you have to treat those. Okay, now important results in countability. First result is the subset of a countable set is countable. Okay, and So to prove this, but the idea is really simple. So let me just quickly go through the idea. So A is countable, which means that I've already listed down the elements A1, A2. They are all distinct. Okay. Okay. Let me also point out that in here, I can assume without loss of generality that both A and B are finite. Okay. Why is that? That's because if one of A or B is finite, then this argument is trivial. But for example, if A is finite, then B is also finite. Then B is countable. And if B is finite, no matter what A is B is also countable. So we can assume without loss of generality that both are infinite. And since both are infinite, in particular A is infinite countable, so I can list out the elements of A as in this fashion. And then that's my A. And then I have to list out, so I have to think about B now. So what I'm going to do, the procedure is going to be like this. So I'll look at A1. So does it belong to B? If it does, then I'm fine. Okay. Else, if A1 does not belong to B, which might as well be the case, then I'm going to move on to A2. And once again, ask whether A2 belongs to B or not. If it is, then I'll stop. If not, I'll go to A3 and keep doing this. The point is that, at some stage, there will be for sure some AN that will belong to B. Okay. So that I'm going to call AN1. So that will be so N1 is the smallest index or the smallest natural number for which AN belongs to B. Okay. That's what this means. Then once I've gotten hold of AN1, I'm going to look for the next element that appears in B in this list. So I'll look for the next AN1 plus 1. If it belongs to B, then I'm happy, or I'll throw it out and move on to the next one. And keep doing so, repeat this process to get hold of the second element AN2 and AN3 and so on. And by doing this, I will have exhausted B completely. And now we have, so this is basically your B. And this is a countable set because there's an easy bijection from N to B now via G of, or G of K is equal to A N K. So the kth natural number is sent to the kth term in the sequence. And notice that the way I've constructed, they're all different. Okay. So those are the two things you have to justify, that, at each step, you're able to find some AN1, AN2, AN3, and so on. And secondly, that you have exhausted all the elements of B by doing this. And both these ideas are clear, but to make it mathematically precise, one has to work a little bit hard. And so first of all, existence of this AN1, AN2, this is guaranteed by something that is called the well ordering principle. And as I've stated in one of the exercise problems, homework problems, that, what is this well ordering principle? It says that every non-empty subset of the set of natural numbers has a smallest element. So we're not going to prove this. Proving this is it requires some amount of logic. Okay, by logic I mean the subject topic logic. So we'll not worry about. So we'll just assume the truth of this principle. Okay, and this principle will let me get hold of those AN1, AN2, etc. And then I have to give another argument to justify that I've exhausted all the elements through that list. So how to get hold of this AN1, AN2, etc. So it's to do that, we'll define this set N1. So to get hold of the first or the smallest index N1, so that AN1 belongs to B, I'm looking at this capital N1, which is going to be all those indices N for which N belongs to B. And definitely this is a non-empty set because elements of B are from A, right? So they'll be of the form A is sub n. So this is a non-empty set. It's a natural, is a subset of the natural numbers, and therefore it has to have a smallest element by that Weyl ordering principle. So existence of those ANIs is guaranteed by this famous. So we had to resort to a strong mathematical principle to get hold of those AN1s, N2s, etc. So at least AN1s so far. Okay, so that's how I get my AN1, and this AN1 I'm going to put it in some basket which I'm calling A infinity for the moment. This symbol, I'll just describe this symbol in a second. Now, how to get hold of N2 pretty much follows the same stuff, except that N1 I have to keep it out of consideration. So N2 will be all those indices for which N belongs to B, but different from N1. So I have to subtract the set N1. So once again, this is non-empty. Why is that? Because my assumption is that B is infinite. And since B is infinite, B minus some set, B minus a singleton is also infinite, and therefore this set is non-empty. And once again, by Weyl ordering principle, I can get hold of this N2, and then this AN2 will belong to B. So that's my next. So I'll put this in this basket infinity. I'll keep doing this, and that means I have to give the so I have to give the construction inductively. So that's what we mean by keep doing this, right? So for each k, I have to specify what am I doing. So after k steps, remember that I've gotten hold of AN1, AN2 up till ANK. Okay, so all these are, so these are the first k elements of B. I have to figure out what the next element is going to be. So that's why I'm looking at this set ANK plus 1, which is a set of all indices, so that once again it's pretty clear in so set of all indices such that n belongs to B minus AK. So B minus AK, AK is the set of first indices which I've already put in that put in the basket, right? So this set is still non-empty. Why is that? Because I'm still subtracting a finite set from an infinite set. So this is non-empty. Therefore, this set is going to have a smallest element, which I'm calling nk plus 1. So that's my inductive definition of the kth element, or yeah, kth element of the set, kth element of the set B. Okay. Okay, and so at every step, just remember that at every step of this AK, whatever, no matter what k is, AK is going to be a finite set, so that B minus AK is still infinite, so that nk plus 1 remains a non-empty subset of it. So that's what lets me use the Weyl ordering property at the kth step to find this nk plus 1. Okay, once I'm done with that, then another mathematical operation lets me put all the information together so that I don't have to, keep doing this again and again till infinity. So that is it. This process of taking union of sets. So A infinity is basically union of all AK. It's, if you can see. So this, you know what I mean. So this. So I put. So I'm putting each time I'm getting some new A and K. I'm putting in here. So basically, so at the k plus 1th level, I'm adding just one more term. So this AK will be contained in AK plus 1. So next term is A of nk plus 1. And so therefore, A infinity is nothing but the union of all the AKs from k equals to 1 to infinity. That's it. So my next claim is that this A infinity, accounts for all the elements in B. So just to be double sure, it's already intuitively pretty much clear. So I have to, because of the construction, right? So I'm not missing out on any element of B. But since we're taking this infinite union and so on, so let's just make sure that we're not actually missing out on any element. So that means I have to show A infinity is equal to B, really. So this is what we have to show. So it's pretty clear A infinity is contained in B because, yeah, elements of A infinity are coming from B, right? By construction. And so to show they are equal, I have to show that every element of B is in fact in A infinity. So I take a random element in B, and this random element is still an element of A, capital A. Remember, so that means it looks is in the form A sub n m, right, over here. Okay, and since it's in this form, so to make sure that those A and K's take care of the whole B, I'll have to show that this M is one of those NKs. That's it. But notice that this NK is, so this sequence NK, if I look at N1, N2, etc., this is strictly increasing sequence of integers. They're distributed. So given this integer M over here, I can always find the NK plus 1, which is nearest to this integer M, and to that, and it's strictly bigger. Okay. And then accordingly, this NK would be something that is lying either on M or to the left of M. It's definitely this NK is not going to lie in between NK plus 1 and M. Otherwise, the choice of NK plus 1 would be wrong. So I'm by choice, by construction, NK plus 1, choosing it to be the term in this sequence of integers that is lying to the right of M and it's nearest to the M. Okay, and strictly on the right. So I'm not letting it. So that means that there's such a choice. So we have used this argument before. So such a choice always exists, right? Like in the case of integers, because this sequence is increasing. Okay, so so I can find this NK such that NK can coincide with M, but M is strictly less than NK plus 1. So my next claim, in order to show that I've exhausted everything, like I said, I have to show that M is equal to NK really here. So if M is not equal to NK, then we have a problem. What is that problem? Problem is that, you know, this then this choice of NK plus 1 would be contradicting. Why is that? That's because, see, how is NK plus 1 being chosen, right? So look at AK, AN1, AN2 up till ANK, and so NK plus 1 is the next one, is the smallest integer that is bigger than NK, such that ANK plus 1 is an element of B. Or in other words, NK plus 1 is the next index that comes after NK, so that NK plus 1 is an element of B. But if M lies in between NK and NK plus 1, that will be contradicted, because then M would be the smallest integer that is such that, you know, AN belongs to this set. See? So NK plus 1 by construction. Okay, once again. So that means this is impossible. Therefore, M has to coincide with NK. Okay, so as an immediate byproduct of this result, we have if A and B are countable, then the intersection is also countable. So this follows. So A intersection B is a subset of, say, A, and since A is countable, its subset is also countable. Okay. Next fact is that union of countable sets, or let me put a finite union of countable sets is countable. So actually, a stronger version of this fact holds, namely that, you know, a countable union of countable sets is countable. So I'm going to prove something weaker here. Okay, so a finite union of countable sets is union. So let me start by proving for two sets, and then by induction it will follow for, you know, n number of the sets. Okay, so so we have to look at a few different cases. and not really hard. Moment I tell you what to do, it will be clear. So first of all, I'm going to look at a case when A and B are disjoint. Okay, and so by assumption A and B are countable, and I'm adding one extra assumption just for the time being that A and B are disjoint. Then I'm going to prove it for the general case later. Yeah, so A and A intersection B is empty, disjoint, and then it's so A is countable, B is countable. Then I'll pretty much follow what I did for integers. We had this negative integers. So I think of that map we defined. Negative integers where even natural numbers were assigned to positive integers. Odd natural numbers were assigned to the negative integers. So I'm going to do this pretty much the same thing. So A is like the set of negative positive integers. B is like the set of the negative integers. So yeah, so I know what to do. So even will be sent to A, odd will be sent to B using the similar idea. So what is that idea? So if n, I'm simply going to send to n over 2 if n is even, and I'll send n to B n plus 1 by 2 if n is odd. So if you write down the terms of this sequence, things will be much more clear. So for example, 2 is assigned to A1, 4 is assigned to A2, 6 is assigned to A3. That means by this assignment, I'm able to exhaust all the elements of A in a bijective fashion. Similarly, 1 is assigned to B1, 3 is assigned to B2, etc. So once again, so this takes care of all the elements of B. Okay, here I think I'm assuming both A and B are countably infinite. Okay. So if one or both of A and B are finite, then things are really easy, straightforward. So I'm leaving that as an exercise for. So yeah. So assumption is that both are countably infinite. That means, so where is this assumption playing a role? So this assumption is playing a role here because see, I'm assuming that elements of B are they're infinite, and already I have a bijection from the set of natural numbers to B. Okay. Yeah. So this assignment leads to a countable. So union of two disjoint countable sets is countable once again, and inductively, union of three disjoint countable sets is also countable. As you can see, I can simply write A union B union C. I'm going to pair up A and B together. And by whatever we have proved just now, A union B is countable. Okay. And so once again, I have basically boils down to union of two countable sets. And therefore, once again, applying the previous result, we have this union as a countable. So it extends to n number of things. Now, in the general case, A and B are countable sets and not necessarily disjoint. Then A union B is countable. How we are going to show that? So just imagine this Venn diagram. So A union B is actually union of three disjoint sets, A intersection B, and B. And all these sets are countable because this is a subset of A. A is countable, therefore this must be countable. A intersection B, once again, subset of A, therefore it must be countable. And this green part is a subset of B, which is countable because B is countable. Therefore, just by whatever we have proved just now, A union, so this union, the intersection union, this part is going to be countable, which means A union B is countable. Next important result is that Cartesian product of two countable sets is countable. So here we have to work slightly harder. So first, I'm going to give you once again, this argument was originally proposed by Cantor, and so A is listed as AN, B is listed as BN. So A cross B, I'm simply going to write down in a particular fashion and then move around this list of elements in A cross B in a certain manner, so that it will be clear to me that there exists a bijection from N to this set. So first of all, how am I listing out these elements of A cross B? So so in the first row, I'm going to pair A1 with every element of B1. In the second row, I'm going to pair up A2 with every element of B. and so on. Okay, so in the first row I have a1 b1 a2 b2 a1 b2 a1 b3 etc. so on. Okay, and now once you have listed things out in rows, I'm going to move in a peculiar fashion. And so I'll start at this a1 b1, which I'm going to call x1. So along the way I'll keep labeling things so that the fact that this gives me a bijection from n to a cross b will be clear. So this one I'm going to call a1 x1, and then I'm going to move I'm going to travel along I'm going to move to a2 b1. Okay, and travel to a1 b2, and then change direction at a1 b3, and then move along a2 b2 a3 b1, and then change direction at a4 b1. So how long am I maintaining my direction, particular direction? So notice that I'm maintaining my direction as long as the sum of the indices are the same. So basically, so here 2 plus 1 is 3, 1 plus 2 is 3, and in the next term 1 plus 3 becomes 4, so it changes there. So I'm going to change my direction accordingly. So 1 plus 3 4, 2 plus 2 4, 3 plus 1 4. I'm going to travel, and then it will change direction at a4 b1. Okay, so some of the indices are now 5, so I'm going to travel along that. So idea is to arrange the elements of a cross b in a fashion so that some of their indices is so to group those elements of a cross b, some of whose indices is a fixed number. Okay, and this set will, for example, for every natural number m, I'm going to look at I'm going to first of all look at all the pairs ai aj such that I plus j equals to m. And so this set will be finite, and I'm labeling this particular set in a certain fashion. Okay, so you can, as you can see, this a1 b3, I'm calling it x4 and x5 x6. So this being a finite set, I can label things the way I want, and then using that labeling to extend it to the whole a cross b thing. Okay, so that's the idea here, Cantor's idea. So so if that idea doesn't work for you, then we have this a second method to understand this. So in this method, we'll first show that this n cross n is actually, there's a bijection from n to n cross n. Okay, so roughly speaking, n cross n apparently has the same number of elements as that of n. And how is, so its proof is really simple. So all you have to do is define a function from n cross n to n. Okay, and so some injective function, that's the plan. So as long as you have a set x, and as long as you have an injection from x to n, then x will be countable. Why is that? That's because then x is similar to a subset. So x being injective, it means that x is, there is a bijection from x to its image inside here, so which I can call, say, x dash. Okay, so x is bijective to its image because this map is injective, and so any subset, so x dash is a subset of n, therefore this x dash is countable, and I know therefore x is countable because x is similar to x dash. So that's the idea. So all you have to do is simply find an injection from n cross n to n, and this is given by this particular map. So f of m comma n is being sent to the power m to the power n. So is this a well-defined function? It's easy to check. You do it, you can do it. It's pretty simple. Is it injective? It's also easy to check. So if you have to show that if 2 to the power m into 3 to the power n is equal to 2 to the power m1, 3 to the power n1, then so if the images are the same, then the inputs must be the same. Inputs are mn, then mn must be equal to dash, this particular thing should imply that mn is equal to m1. And like I said, two pairs will be equal, so that when m is equal to m1 and n is equal to n1, that means you have to show that if this holds, then this implies this condition, and this condition in turn will imply this. Okay, now try to prove that. Just switch around that. I mean, you put the 2's together, 3's together, and see if you can use some arithmetic to show that this map is injective. So that takes care of n cross n. And next point is that, how we are going to use that. N cross n is similar to n to say that, if a and b are countable, then a cross b is also countable. That's because, if a is countable and b is countable, then that means you have a bijective map from n to a, and you have a bijective map from n to b as well. Then you can club these two together. There's a way to pair the functions f and g together to get a bijection from n cross n to a cross b. And we already know that n cross n is already bijective to n. So this bijection H will prove that, by that similarity thing, this n cross n will then be, this a cross b will be similar to n as well. Okay, so what is this map? Once again, it's pretty simple. So so this am is simply f of m and bn is simply g of n. Okay, I did not mention that here yet. Yeah, so my map is quite natural. I'm just simply going to use the map that I already have, this map, these two maps, f and g. So h of m comma n will be defined as the first m will be sent to, I have to send it to some element of a. So definitely I'm going to send it to am, and this n I'm going to send it to bn. So this map, once again, is a well-defined bijective map. Check that for yourself. So this proves that a cross b, if a and b are countable, then a cross b is also countable. Finally, we are about to show, using all these techniques, that Q is countably infinite. So how am I going to write? So first of all, so it's enough to, I'm saying that it's enough to show that the non-zero rationals form a countably infinite set. That's why is that enough? Because if Q star, the set of all non-zero rationals, if this is countable, then Q is simply Q star union 0, right? So union of two countables is countable. So I can deduce that Q is countable from there. So it suffices to consider only non-zero elements of Q. And I can write them as a ratio of two integers, a and b, with the, the product AB is not equal to 0, right? Because it's a non-zero rational number. And on top of that, I can assume that GCD, A and B are relatively prime to each other. So basic idea is that, I'm going to paste this Q star inside some set which I already know from before that is countable. So Q star, I'm saying, injects to this. So Q star, which consists of this A by B kind of objects, it injects. So I can find an injection from Q star to this particular set, which consists of, so this AB, I'm going to send it to A comma B. That's it. And all the conditions are just the same. But notice that if I do, so if I can somehow show that this map AB being sent to A comma B with these properties, of course, with these restrictions, if I can show this is an injection, then I'm through. Because this set, whatever it is certainly a subset of Z cross Z, right? And Z is countable. Z is also, so Z is countable means that Z cross Z, we have just shown that Z cross Z is also countable. And this being a subset of a countable set will also be countable. And Q injects into it. That means Q actually bijects onto it. I mean, it does, So basically, point is that Q is injecting into a countable set. Being injective into a countable set means that it is countable, as we have argued before. So, so all you have to do is show that this map sending A over B to A comma B is bijective or injective, not even bijective. Injective is enough. And for injective, you look at, so here I checked whether it's well defined or not. So once again, that's a good exercise for you. Okay, try to show that this map is well defined, which means that you show A by B equals to A dash over B dash. That should imply from here you should be able to deduce that A comma B is equal to A dash comma B dash. And so basically doing this little calculation over here, all I'm doing is showing that if this is given, from here, I can show that A is equal to A dash and B equals to B dash, which would mean that A comma B is equal to A dash comma B dash. And that is the plan right? Yeah. Okay, now showing that F is injective. So I have to now assume that the images are the same. And from there, it should follow that A over B is equal to A dash over B dash. And this is actually simpler, okay? Because by definition, so f of A over B is being mapped to A comma B. A dash over B dash is mapped to A dash comma B dash. So two pairs are, so their images are the same. That means if these two pairs are the same, then of course it means A equals to A dash and B equals to B dash. And then if A equals to A dash, B equals to B dash, then A over B must be equal to A dash over B. So injectivity is easier to establish than showing that the function is well defined. So try it out on your own first. So we're through. Final piece of the puzzle is showing that R is uncountable. And as one of you have indicated already how to proceed on with this. So first of all, I'm saying that to show that R is uncountable, it is enough to show this closed interval 0, 1 is uncountable. Why is that? Think about it. Okay. So showing this is uncountable is enough. Okay. So, and let's take advantage of the fact that everything in 0, 1 can be represented as 0 point. So I'm looking at the decimal representation of each of those numbers. So as once again, one of you said, I'm going to use that word verbatim, the sentence that pretend as if I is countable. That means I can list down the elements of I as x1, x2, etc. And for each of these, I'm going to write down the decimal expansion. So being an element in the closed interval 0, 1, I can write them as x1 equals to 0 .d11, d12, d13. x2 is d 0 .d21, d22, d23. So these are digits. So these are from 0 to 9, right? These digits. Similarly, x3 and xn is some dnn. So d starts with dn1, dn2, dn3. Then we have dnn, and then dn n plus 1 and continues. You have this, right? Now, the trick is to form another real number that lies within the closed interval 0, 1, but is not listed in this list. How do we proceed to do that? So as I've circled here, I'm going to look at the numbers that are appearing. So look at the number appearing at the top left, D11, then look at the second number in x2, or second digit appearing in the expansion of x2, D22, third digit in the expansion of x3, x33. So I'm getting a diagonal kind of sequence here. And then after doing this, I'll simply change the digits a little bit. Okay. So for example, if D11 is say 5, I'm going to change it to 7 or something that is different from 5. So here I'm simply choosing the easier way. So how am I changing this DII? So look at this number. So D11, D22, D33. So I'm changing DII to DII dash by simply adding 1 if DII is not equal to 1 and subtracting 1 if DII is equal to 1. Okay. So this changes the digit DII. And then I'm looking at the real number x, which is given by 0 point D11 dash, D22 dash, notice that I've changed, yeah, D11 dash, D22 dash, D33 dash, etc. Okay, DN dash. And my claim is that this number, oh, of course, it's in I because it's 0 point some decimal digits. Why is it in I? We'll probably will be able to answer that after. So this is basically by comparing with a geometric series, you can show that this number belongs to the closed interval 0, 1. Anyway, the point is that next, the key idea is to show that this belongs to I, but this does not appear in that list. Which list? This list. So this list consists of, so like I said, this list exhausts this interval I. And if I can show that number x that I've constructed in this fashion is not in this list, then that will be a contradiction, because my assumption is that everything in I is one of these. So why is this X that I've constructed over here is not an element there, is not in that list? That's because if it were, then this 0.d11 dash d22 dash, this number will be equal to some xn, right? So if x is equal to xn, then this number should be equal to this number. But now we are going to strongly use the uniqueness of this decimal expansion. So every real number can be uniquely expressed as a decimal expansion, of course, under the convention that you have 0.9999, so that is equal to 0. You have seen this before, so this is equal to 1. That's the only convention. Okay, so if it helps, we can even we can actually take the open interval 1. So 1 is not an element, so this ambiguity is not there. So even if you get 0.99999, so this definitely, yeah. So let's use this. So once I've removed this 9 or 1 from this my initial interval, so this ambiguity is now not there. Now you can say that every number x in that interval has a unique representation, and so uniqueness means that these two numbers, whenever 0 point something is equal to 0 point some other thing, so then digits are equal component wise. So this in particular will mean that d11 dash equals to dn1, d22 dash is dn2, and in particular dnn dash is equal to dnn. But this is impossible because of the way we have constructed that dnn differs from dnn dash by 1. So they are not the same. Okay, so that's pretty much the proof. Okay, so this diagonal element here, they don't match up. Okay, so let's see what sort of questions you get from here. I think I'll stop there.